introduction and also for the invitation to come here. I always wanted to come to Taiwan, but I have never done it, and this is my first time, so I'm excited to be able to eat Taiwanese food and also to discuss with you guys. The first surprise was that the breakfast today was delivered, and it was just hamburger from McDonald's. It's strange. Strange room service. I was expecting some even some kind of nice breakfast. That was also fun. Okay, so I'm going to give lectures using slides. This is something I have never done, so I'm not sure if I do well with time. I was just lazy, and I thought that it's good to just combine my old slides to make lecture slides. Then I can save time, but actually it turns out to be more time-consuming than making handwritten notes. But anyway, that's that. You don't care about that. Okay, so a microstate geometry program is Superstrata. So microstate geometry program, if you know it, is about constructing microstates of a black hole in terms of classical gravity solutions, and it is to some extent successful, but it's not fully successful in that sense, in the sense that it has not reproduced the black hole entropy. But these are really nice solutions, and the program is interesting, so I want to explain this, and also I want to discuss some new solution of the microstate geometry type called Superstrata, if I have time. Okay, so the plan is to first explain what you mean by black hole microstates, and then I will talk about microstate geometries, and then I will mention the Fuzzball conjecture microstate geometry program itself, and then I will explain some examples of microstate geometries. Okay, that's the rough plan. I have time to follow this plan. So I will first briefly explain the things I wrote here. So what do you mean by a black hole microstate? So a black hole is a black thing like this, and we think that this is representing a thermodynamical ensemble. So there are many underlying microstates, and you have something like this. So if this is a canonical ensemble, and you have some density matrix with finite entropy, and this black hole is believed to represent such a density matrix. But of course, if you have an ensemble, it is made of individual microstates, and you wonder what then is the individual microstate represented by. So what is it? So that's the question, and this is what I mean by the microstate. And this does not have to be a solution of supergravity. It can be fully stringy, but well, there should be something like that. And okay, next, what are microstate geometries? Okay, so I talked about black hole microstates, and they are in general expected to be stringy. But in some cases, it is known that there are some microstates which are described by smooth horizonless solutions of classical gravity. So normally you would think that a black hole is a geometry like this. You have a throat, and there's a horizon, and in the deep inside, you have a singularity. But there are some solutions which are completely smooth and have no horizon, and this has the same asymptotic charge mass as this black hole, so this should be regarded as a microstate. So although this is a classical solution, this is a microstate, and it's interesting that such a thing exists. And also what's interesting is that this has a finite spread. And this is actually a very counterintuitive thing, because if you put, okay, and also, sorry, I forgot to mention, but this spread is becoming larger and larger as you put more energy to the black hole. And this is a bit counterintuitive, because whatever structure you have, if you put more energy, you think that the gravitation becomes stronger and the structure is expected to shrink. That's the intuition from gravity, but it's not happening. And somehow, the more energy you put, the bigger the spreading becomes.
So
yes?
That's an object as a velocity.
you ask if this is a pure state. It is a pure state. It is regarded as the coherent state of the microscopic underlying microscopic theory. Yeah, this should be a pure state because there is no horizon and there is no way to associate an entropy to this. Okay, and the Fuzzball conjecture, the third thing I mentioned in the plan is the Fuzzball conjecture, and this is a conjecture about whether this is a general thing. So conventionally, you have some black hole, but are all the microstates described by some kind of fuzz thing, which is spreading across a horizon scale, and somehow this has no horizon or singularity. And okay, so black hole microstates are some stringy configurations spreading over a wide distance. Can that be true? So this is a question. And the microstate geometry program is asking how much of such black hole microstate geometries, so how much of such black hole entropy can be accounted for by smooth horizonless solutions of classical supergravity? So in general, you think that the microstates are stringy, but there are certainly some microstates which are represented by classical gravities, and how much of black hole microstates are described by such classical things? That's an interesting question. The answer may be one, or maybe maybe the full entropy can be reproduced, or maybe only measured zero set can be reproduced by the classical geometry, but it's still an interesting question to ask.
There is also the possibility to probe something beyond classical gravity in this program.
Well, the program itself is defined as a classical thing, so it's, by definition you can. But if you, at the same time, the problem is that you don't really have tools to go beyond.
I see.
Yeah, by going beyond, you have to consider stringy modes.
Yeah.
So supergravity is the massless sector of strings, and if you want to include higher modes, massive modes, then you can go to maybe string field theory. But I don't know if you have the technique to do that. Yeah, recently there was some claim that they have constructed the full flow string, the flow string. There's some claim that they have constructed the super string field theory. So maybe they can be used, but yeah, that's not what I talked about here. Okay, and what is the Superstrata thing that I also mentioned? So this is a new class of microstate geometries for some particular free-charge black hole, and this is the most general class ever known with known CFT dual. And so this is nice, and we have explicitly constructed basic superstrata solutions, but this is not enough, and this does not reproduce the entropy yet. So we have to consider more general ones to reproduce the black hole entropy, if it's possible. And that's the recent progress that I want to mention at the end of these lectures. So these are the ingredients of the lecture. So if there's any question.
I have one question. So if we have a low energy probe coming towards this configuration,
right?
Well, will they still experience a semi-classical horizon in the sense of the equivalence principle, or is it going?
How low is the energy?
Far below the Planck scale, but perhaps on the order of, say, the horizon.
So it's falling from infinity.
Yeah.
Then it becomes really high energy thing near the horizon, right? So the honest quick answer is I don't know, but it's a very non-trivial question, and maybe if you are really high energy object at the horizon, so even if you are a low energy guy at infinity, you will become a high energy object near the horizon, and I don't know if it's going to feel the structure or not. Maybe not.
Well, yeah, that's my general question. If we tune the energy so that it's low enough that can be, I mean, does the existence of a fuzzball mean that that a low energy observer still, I mean, will a low energy observer pass through the horizon without seeing anything, or will they suddenly have a problem with the horizon?
I think
According to the Fuzzball picture.
I think if you're a reasonably low energy guy, then you're not going to experience anything because you're going to be high energy near the horizon. But if you're a really, really, really low energy guy, then you're going to feel the existence.
What, so the regime where classical general relativity is supposed to be better is where. The regime where classical general relativity is supposed to be better is where you don't expect there to be a classical horizon. Something dramatic is going to happen to an observer at low energies who passes through the horizon.
Yeah, when you're low energy near the horizon, even near the horizon, then yeah.
How is that?
You must feel.
Well, why is that compatible with the equivalence? Okay, one second. So in other words, is there a firewall in the Fuzzball picture or not?
I guess that depends on the probe. And for a low energy guy, I think it should feel difference.
But what should we do in this picture to answer the question? In the Fuzzball proposal, what should one do and calculate to answer this question, which is important?
Yeah, there are some. You can answer. Try to answer that question even for the LLM geometry, right?
Yeah.
Yeah. What's that answer to that question?
I would just say we can use like 1950 style general relativity and say nothing happened. But apparently that's like a controversial statement now.
Or maybe something will happen if you sum over all the geometry. And then, like in statistical mechanics, if you go to large volume limit, sometimes you have some singularity.
That's correct. So I would imagine that if there's a large degeneracy of states, that an individual probe will not actually experience.
So maybe one thing we want to do in this program is to try to isolate the singularity in doing this partition function.
Yeah.
And maybe you can then identify the horizon in this way.
Yeah.
Like this Yang-Lee singularity in statistical mechanics.
Maybe we can postpone that.
Yeah, sorry, I didn't want to.
Well, but that's an interesting question. That's an important question.
But nobody's actually done like an explicit calculation.
I don't think so. Yeah, there are some rough computations by Samir throughout the world, but I don't know if it's not real concrete thing using concrete Fuzzball solutions. So I don't think.
Yeah, but even Matour's answer seems to have fluctuated somewhat. At first he was saying that yes, there would be a firewall, and then he's saying no, maybe not.
Yeah.
If you do this thing where you take into account there's a large degeneracy of states, so that's why it's kind of unclear in my head.
But I think the most recent opinion is that if you're high energy enough, then although you're going through the fuzz thing, you're somehow his experience is that you're not going through the fuzz, but you're really experiencing the flat space.
Yeah.
And if you're a low energy guy, then you're experiencing something. Yeah. That low energy thing is completely true, right? Because if you have an LLM geometry, so you have some bubbling geometry, and if you're lowering maybe D3 rank or something, then it should feel what is there. Because you have to be able to feel the bubbling structure if you're D3 rank. You have EBS with the background, and you can be exploring a really short density structure, short distance structure of the geometry. But if you're a usual guy and you're just a string that falling into that thing, that's a different question. Yeah, I don't know what is really happening. And naively you would think that nothing happens, but I don't know. I haven't done the computation, so I can't really say that for sure. Okay. Any other questions? So black hole microstates, that's the first thing. So the black holes are, as you know, this kind of thing with an event horizon and empty space inside, except for a singularity here. And it's a solution to the Einstein equations. And the event horizon is here. Space-time singularity is where space-time description breaks down. Okay, we know this. And the classical aspects of black hole is really well understood. So if you like to simulate the process in which two neutron stars merge together to form a black hole and what kind of gravitational waves emitted, that you can compute without any problem in principle. Well, maybe if I say this to real GR simulation guy, then he would be angry, but there is no in principle thing, no matter how difficult it is. Okay, and on the other hand, quantum or microscopic physics is really not well understood, and there are various puzzles. And one thing, for example, is the black hole entropy puzzle. Black hole entropy is, according to vacation Hawking, is given by the area divided by 4G Newton. And if you believe in the statistical mechanics, this means that there are many microstates given by e to the black hole entropy. And for black hole with solar mass, this number is like 10 to the 77. So the entropy, sorry, the number of microstates is huge. On the other hand, there is the uniqueness theorem, which says that given the black hole mass and charge, there is only one solution. Then this seems to suggest that there is only one state in this system. So how can they be consistent? And the discrepancy is huge because this divided by this is 10 to the 10 to the 77, for example. On the other hand, the cosmological constant problem, the big problem, is like 10 to the 120, which is really, really tiny compared to this. Okay, so this is a bigger problem, right? Okay, anyway, so where are these microstates? So the uniqueness theorems seem to be obstacles to this, but we know that we are not living in, well, string theory says that the space-time is not 40, but we have more dimensions, then this can be avoided. So the uniqueness theorems of the form we know is for 4D, and if you go to 5D, then there is no uniqueness there. For example, there are black rings. So you can go to higher dimensions, so this you can avoid. But on the other hand, you think that if you want to really understand the microscopic structure of a black hole, then we need quantum gravity or string theory. And we don't really know what exactly quantum gravity or string theory is. We only know the perturbative definition of string theory. So what can we do in this situation? Okay, what you normally do, one way out, is the ADS-CFT correspondence. So string theory or gravity in ADS space is dual and equivalent to certain quantum field theory living on a boundary. So we can use this to define string theory or quantum gravity on this side. So if you can use this, then you can, in principle, study black holes in the full string theory or quantum gravity. So that's nice, and that's what people did. For example, what Stromich and Bappa did in almost 20 years ago. If you have a string theory gravity in ADS space, and you have a black hole in this, so you have something like this, then this is supposed to correspond to a thermodynamical ensemble on the QFT side. And thermodynamical ensemble in QFT is a real simple thing. So you can just compute what the entropy is by really exclusively computing the, counting the microstates. And you get some CFT entropy, and this surprisingly agrees with the Wittgenstein-Hawking entropy for the bulk black hole. So this work has put the statistical mechanical interpretation of the black hole on a firm ground. And some fine print, actually Stromich and Bappa predates ADS-CFT, so they did not really use ADS-50 in a strict sense, but this is a modern interpretation of the board. And also one thing, you may think that for this argument to hold, you have to use supersymmetry, and you have to use the supersymmetry prediction that says that the states in the weakly coupled side is never lifted, even if you go to the gravity strongly coupled regime. But you don't have to use it for 2D CFT, because even for strong coupling, you can use the Hardy formula to account the entropy of the CFT, and this agreement holds. Anyways, all I'm saying is that using ADS-50, this is a real firm state. Okay, now, so that's fine, that's great, but what about microstates? So you have a black hole here, and this corresponds to a thermodynamic ensemble. And if you have a thermodynamic ensemble, then this is composed of many individual microstates, like this psi. Then what is this? What is this on the gravity side? What is the microstate in the gravity picture? So that's the question. And in general, you expect that this is a state of quantum gravity or string theory in general, and not describable in classical gravity, for example.
Sorry, maybe
Yes.
a stupid question.
Yes.
But since you are using ADS-CFT, this kind of reasoning applying only for black hole in ADS.
Yeah.
So
for in this context, yes.
okay. Okay. But you think that this can be generalized to
General, black holes in flat space. Okay, and here by gravity picture, I mean the bulk side of the ADS-CFT corresponding. So on this side, and I don't mean the classical gravity. Just to make sure. And so to summarize, what we want to know is the gravity picture of the black hole microstates. And again, by gravity picture, I don't mean the classical gravity. It can be fully string. Okay. Now, microstate geometries. So I talked about general microstates, but some are described by geometries, classical gravity. Okay, so the question is, are any examples of gravity microstates known? So I talked about gravity microstates in general, and they are in general require full string theory. So they involve all string oscillators, whereas G mu nu, B mu nu, B mu nu, dilaton, fields, these are only massless truncations of the whole theory. So here you have this gravity, which classical gravity, by which I mean only the massless truncation. Then you don't think that this can be described. Sorry, you don't think this can describe the general microstate. However, there are some examples for which microstates can be described by classical solutions, microstate geometries. Okay, so there are examples of microstates called microstate geometries, and they are solutions of classical gravity, and there is no massive string mode in that. And also, it has the same mass and charge as the black hole that you want to represent. And it has smooth and horizonless geometry, and many are just for supersymmetric black holes, but there are some microstate geometries which are for non-supersymmetric black holes. Okay, so as some examples of such microstate geometries, I want to present some geometries. First one is the LLM geometries, Lin-Luli-Malesner geometries from Superstrata 4. And this is one of the first examples of microstate geometry. This is not the very first, but this is one of the first ones. And this is the microstate geometries for the system of ND3 branes, and you preserve 16 supersymmetries out of 32. Okay, so in this case, for this geometry, you consider radius 5, 1/2 BPS sector. So we consider supergravity in ADS 5/5, and if you ask what is the solution, black hole solution for 1/2 of BPS sector, then it is known that the solution is something called a superstar. Super just means the supersymmetric, and it's a point-like object, and it's actually singular. So this is not the actual black hole, but it's a singular element of the black hole. So you make the size of the black hole smaller, and then when the area is 0, then this is still singular, and it is called the superstar solution. And okay, so this is supposed to represent the 1/2 BPS sector of the theory. And if you go to the superior side, so D equals 4, N equals 4 superior mills, then you have, and you're supposed to consider an ensemble of 1/2 BPS states, preserving 16 supersymmetries. And it is known that this sector can be described by n free fermions in harmonic potential. So this is the simplest possible system you can think of. So you're putting, okay, so this is the phase space of this free harmonic oscillator. And if you have just one particle, then it's going to just rotate like this. But if you have many, many particles, so because these are fermions, you can occupy the same state. So at large n, the state must be represented by droplets on this phase space. So in this black droplet, you have all the states filled, and here you have nothing, and in these droplets you have fermions as well. Okay, so this is the large n description of the free fermion system, and it turns out that for each such droplet diagram, there is a solution, smooth solution called the LLM geometries. And this involves no string modes because this is just a solution to type 2b supergravity. So here is a nice correspondence, and I'm going to explain this in some more detail. I'm sorry.
What is the relation between the superstar and this LLM?
LLM geometries are the microstates for this superstar. Superstar is it's a singular black hole. So at the classical level, the area is 0, and you can't see the entropy at this gravity level. But microscopically, you're expecting that this is somehow representing some ensemble, and the ensemble is the ensemble of the geometries. I will have more to say later. Okay, so some more details. So on the CFT side, you have free fermions. Okay, so half BPS states are n free fermions in the harmonic potential, and that was argued by Bernstein and Corey, Jedecki, Van Buren. Okay, so the one particle Hamiltonian is this, and if you have just one particle, then you're just rotating on this plane like this. And yeah, so if you consider a coherent state, then you're rotating like this. Of course, the ground state is just a Gaussian packet over here, but if you consider a coherent state, it will be rotating like this. And if you have a large number of particles, then, as I said, it should be described by droplets in this one particle phase space. Right? Okay, and corresponding to each such droplet picture, a diagram, it is known that they have Lin-Monod constructed geometries, and the metric is like this. And there are some more details